7-4 solving log equations. You'll see some of the first questions. It's based on what we learned in 7-3 about changing it from log to exponential functions. And then the second part of this is using logs to solve some harder exponential equations. All right. We first need to rewrite this in exponential form. So this is what we talked about yesterday. So number 1, how would we write that in the other form? 7, right? Raised to the, raised to the second power is x. Remember, this part is the exponent. Seven is the base. This is the base. The output of the log is the exponent equals x. So this one, x equals 49. All right, number 2. How do I rewrite it? Well, this time the base is x. X raised to the 3/2 is 27. Okay, so from prior knowledge, what does this fraction exponent of 3/2 mean? Square root of x raised to the... Okay, how do I solve this nice little equation? I could square it. Why not just square it? Why not just raise it to the 2/3? I'm solving for x, right? X to the first power. How can I make this to the first power? Raise it to the reciprocal, or 3/2. In the last lesson, we did it like this, right? Remember I talked about this? You can raise it to the 2, and it would cancel those out. Well, it's 2 because it's 2/1, or the reciprocal of that fraction. So we're going to raise this to the reciprocal, which is, remember I'm solving for x, and now it's actually an equation. I'm going to say raise this to 2/3, raise this to 2/3. These would cancel out, or be a power of 1, a product of 1. So x to the first power equals 9. Yes, how'd you get that? You put it in the calculator, all right. Or, guys, we should know from prior knowledge that this means the third root of 27 squared. Third root of 27 is 3. 3 squared is, did you say 9? Okay, so let's go back. The first thing I did is rewrite it from log form to exponential form. I have an equation because there's an equal sign there, right? How do you solve this equation? Well, I have to get this to x to the first power. Okay, so all I did was raise this to the reciprocal. And then I evaluated this. Okay, lots of prior knowledge going into that one little problem, right? Yeah. Okay, number 3, how do I rewrite it? The base is x. X to the 0 power equals 2. Everybody look at that problem right there. How do you solve for x? You can't. How come? Yeah, anything to the 0 power is 1, and 1 is not equal to 2. So what's our solution?
No solution.
No solution. Because this, remember, this is 1, and 1 is never equal to 2. All right, number 4. Again, just rewriting it into the other form. So this would be 2 raised to the x equals 64. Oh, looky here. 2 raised to what power is 64?
6.
6. Very good. I just looked at my chart. Okay. So in these first 4 problems, we took what we did yesterday. We wrote it in the exponential form first and then figured out what the x would be. But as you notice, each x was in a kind of a different position. which created a different little equation at the end to solve. All right, number 5. Oh, this one looks a little bit different. Now I have an expression, don't I? Okay, but again, let's write it in the exponential form first, okay? So how would I write this? 2.
Raised to x minus 9.
No, which one's the exponent?
4.
The 4. 2 raised to the 4th power is x minus 9. 2 raised to the 4th power is whatever is left, x minus 9. All right, 2 to the 4th power is 16. Remember, I'm solving for x. It's a regular equation, so 16 equals x minus 9. X equals 25. Look, if I plug this back in, 25 minus 9 is 16. 2 to the 4th power is 16. All right, what about number 6? Look at number 6. Okay, I have to get the log expression by itself. Just like a regular equation, you've got to get x by itself, right? Well, the x is inside this nice little log expression. If we're going to get this by itself, just like I do in regular algebra equations, okay? So I'm going to subtract 15. I'm going to subtract 15 first. So this is 2. Now 2 times the log base 2 of x equals 10. Again, I've got to get x by itself. So divide by 2. Now can I rewrite it in the exponential form? Basically, I have x by itself. Okay, how would I rewrite this? What does it mean? 2 to the 5th power is x. Oh, yay! So now all I have to do is x equals 2 to the 5th power, which is 32. Okay, that's not too difficult. Everybody good so far? I got the log. I had to get x by itself. I'm solving an equation, but I had to get x, actually this nice little log expression that contains the x by itself. And then I rewrote it, solve for x. Okay, number 7. What do you notice about number 7?
It's got 2 logs.
It's 2 logs on each side. Are they the same base?
Yeah.
Okay, so what's your thought? What did we do before when the bases were the same? No, what did we do before when the bases were the same? When we solved exponential equations, what did we do? We got rid of it and just set the expressions or the exponents equal to itself. It's going to be the same thing here. Okay. The only thing I have on this side of the equal sign is a log expression. And the only thing I have on this side of the equal sign is a log expression. And they're both the same. Okay? So I can drop those and just solve this nice little equation. 4 minus p equals negative 2p plus 2. Kind of the same idea with common bases. Once we got the bases the same, remember we set the exponent expressions equal? Same thing here. Only because these have the same log base of 15 and there's nothing else added or subtracted to it. All right, so now, let's see. I'm going to move this over here so that my variable's positive, and then subtract 4. Is it 1p equals negative 2? Agree? Yeah? Is number 8 set up the same way? The only thing on the left side of the equal sign is a log expression. There's nothing else added or subtracted to it. Same thing on the right side, and the log bases are the same. Okay, so I can cancel those out and say negative 3x minus 1 equals negative 4x minus 4. Negative 3. Does that sound right? Yes? Okay. I can also check this. So if I plug in negative 3, that's going to be positive 9. Minus 1 is 8. Is that going to be the same thing over here? If I plug in negative 3, that'd be 12. 12 minus 4 is 8. Do you see why that works now? They're both the same when I plug in x. They're literally equal on both sides. Okay, so those are kind of the basic kind of questions. Everybody understand? The first page, you rewrite them in the other form and figure out the x's are in one of those 3 different positions. Here I got the logs by themselves. This one that you can drop the logs and solve a simple equation. All right, now let's look at the next topic. How do I use logs then to solve some different exponential equations? You can use what's called common logs, okay, which is base 10 to solve equations containing a variable in the exponent. You do this by what's called taking the log of both sides. I'll show you that in a second. So, common logs. Okay, first thing we have to know, okay, in math, a common log is anything with a base 10, okay? So anytime you see an expression like this that doesn't have a base written in the log expression, it's understood to be base 10. Everybody got it? Anytime you have a log expression and there's not a value here or a base, it's understood to be base 10. Kind of like an exponent of just x is understood to be 1. So in the log world, this is understood to be base 10, and it's called common log. And it's the only way your calculator can take logs is if it's in base 10. Right? How can calculator do all these different kind of logs if every base is different? Right? So the calculator only uses what's called common log. And there'll be lots of applications for common logs that you'll use like in pre-cal and calculus. Right? Base 10. Right? So, for instance, if it's written like this, log of 10 equal to 1, well, it's because 10 to the first power is 10. There's an understood base 10 here. 10 to the first power is 10, right? If it were written like this, log of 100 equals 2, it's because 2 squared is 100. Okay, just know when you hear the phrase common log, that means the base is always 10. All right, and we're going to use that then to solve some different kind of exponential equations. Look at my first problem here. How did we do this in another lesson in this chapter? What did we do? We tried to put them down to the same base, right? Try to put down to the same base, and then we dropped them and then solve for x. But can I do this here? No, because 30, there's no way I can write the number 30 with a base 3. So we're going to use logs in order to solve this. Because remember, logs are what an exponent is to make an expression true. A log is what is the exponent. So I can use logs then to solve this different kind of exponential equation. Okay, this is the way it works. Are y'all ready? Okay, so what I'm going to do, I'm going to take the log of both sides. So please write, I'm solving for x. So what happens is I'm going to move this exponent to the front. So x times the log of 3 equals the log of 30. So literally, I'm taking the log of both sides. So I'm going to write log of 3, log of 30. I'm solving for x, right? So I'm going to move the x to the front. Now, to solve for x, I'm just going to divide both sides by the log of 3. Okay, and because this is common log or understood base 10, I can type this in my calculator literally exactly the way it looks. Y'all ready? So I'm going to type in, look guys, log of, oh, look, I wrote it twice. I wrote 30 twice, didn't I, guys? This is 3. So I'm going to type in log of 30 divided by log of 3. Y'all see the log button? Log of 30 divided by log of 3. And you're going to get a decimal. And this particular source says round it to 3 decimal places. So 3.096. 3.096. Everybody see that? So what we have done is found an exponent as close as we could to make this expression true. Because it's not going to be just a regular exponent, right? Because these aren't going to have the same base. So look what happens. If I raise 3 to my value, it's going to be really, really close to 30. 3 to the third, guys, is 27. So 3 to the 3 and a little bit more is going to get us really close to the value of 30. 3 raised to, what was it? 3, and we rounded it. Remember, we rounded it, right? 3 point, what is it? 096. Pretty close to 30. Look. Everybody knows it's not going to be an integer. This value of x could not be an integer because there's nothing that I can raise 30 to get an integer of x. Like 3 to the third, 3 to the fourth. It's going to have to be a decimal value. And the only way to find that is by using logs in the calculator. All right? So that's literally the process we're going to do every time. Once we get that base with the exponent by itself, then I'm going to take the log of both sides. Okay, so number 2. Okay, just like any other equation, you have to get x by itself, which is that. So I'm going to add 4 to both sides first. So 10 raised to the x equals 38. Now what we're going to do is we're going to take the log of both sides. And when I do that, guys, I'm solving for x, right? So I can do this. So log base of 10 equals log of 38. And then I'm just going to solve for x. And divide both sides by the log of 10. Common base log of 10. So in my calculator, it's really this easy. Log of 38 divided by, oh whoops, I better put a parentheses. I don't really know, but I'm going to put a parentheses just in case. Log of 10. What do we get? 1.580, if we're rounding to 3 decimal places. Wouldn't you agree? 1.580. Here, I'll write it in blue. 1.580. All right. Number 3, same thing. Going to get x by itself. Five to the x equals, what is that, 7? If I could change 7 to a base of 5, I wouldn't even have to use logs. That's what we did earlier in the chapter. Everybody understands that, yes? If I can write 7 to a base of 5, I wouldn't even have to use logs. Okay, but because I can't, I'm going to take the log of both sides so I can actually do it in the calculator. Right, so this is easy. So the x can come to the front. Log of 5, log of 7. What's my x? Just do it in the calculator now. Log of 7 divided by log of 5 is about 1.209. Now I can check my answer, guys. I can put this back in the calculator as 5 raised to the 1.209 plus 14. Now remember, we rounded this off because this is an irrational number. So if I check it back, it might not be exactly 21, but it's going to be as close as we can get it. 5 raised to the 1.209 plus 14. Yep, pretty close, all right? 21? Look at that. Everybody getting the idea? You're going to do the same thing every time. Let's see if any of these are written any different. Oh, yes. Take a look at this one. Am I on the screen up there? Okay, what am I trying to get by itself? This, right? Okay, so just like any algebra equation, subtract 4. So 3 times a half raised to the x equals 15. Divide by 3. So a half raised to the x equals 5. Okay, I can't write 5 as a base of a half. So you're going to take the log of both sides. So the x comes to the front. Log of a half equals log of 5. Everybody see what I'm doing? We're doing the same thing every time, right? Log of a half. Let's see. What does this come out to be? Log of 5 divided by, I'm going to write that as 0.5 just to be safe. Negative 2.322. X equals negative 2.322. Someone tell me why we came up with a negative number. Yes, because it's a fraction. Yeah. So if this is negative, what does it do to this base? Flip it around, right? Flips it to reciprocal. So then when I do the multiplication and the addition, I end up with a regular value greater than 0. Very good. All right. Anything different about number 5, the way it's written? No? I don't think so. Can I go ahead and take the log of both sides the way it's written as is? Yes. There's nothing added, subtracted, multiplied to my base here. So take the log of both sides. This comes out in front. 4x times the log of 2 equals log of 3.6. I'm going to divide both sides by the log first, guys, okay? Got to get rid of that. I'm trying to get this by itself. So I'm going to do that first. I guess that's why this one's a little different. I'm left with 4x equals about how much? Anybody? 1.848. Yes, it's irrational, right? 847 something, something, something. Just take that value in your calculator and then divide it by 4. And we'll get a pretty good estimation. It's approximately how much if I divide that by, can y'all see? Oh, I'm so sorry. Y'all can't see my work. Okay, so this one's a little bit different. I had to divide by the log first. I'm trying to get this by itself. I'm gonna divide by the log first to get rid of those logs, and then divide by 4. You get about I got about 0.462. Agree? Did y'all do it in your calculator? Okay, let's see how that comes out. So if I did the math in my calculator, if I'm checking my work, 2 raised to the 4 times about 0.462. Is that about 3.6? Oh, wow. Check that out. Pretty close. All I did was substitute that number in for x. Look how close that is. Okay, last one. Is this base by itself? Yep. Okay, so now this exponent comes out in front. Take the log of both sides. So log of 19 equals log of 3. I'm going to divide this off first so I can get this down to a regular value. Some real number, x plus 4 equals, oh geez, I have to use my calculator.
0.373.
Log of 3 divided by log of 19. And if you want to just leave this up on your screen and then just subtract 4, that's what I would suggest. And then just round it at the very end. Subtract 4 to what I got there. I got negative 3.62, what? 7? Okay, again, I came up with a negative number, but I don't see a fraction in this one. Why is this one okay to have a negative number? I'm just thinking about the reasonableness of my solution. Yeah, if I plug this back in, negative 3.6, and I add 4 to it, it's going to be a positive number, isn't it? A really small one, and that's why 19 raised to a really small fraction, it's going to end up to be a smaller base of 3. Got it?